Today we are going to discuss the last topic of this course, and the topic is third isomorphism theorem. So the statement of this theorem is H and K, these are two normal subgroups of a group G, and H is the subset of Q, K. Then we will show that the quiescent group over a quiescent group with G upon H with K upon H is always equivalent to another quotient group G upon K. This is our target, and as you know that this is a specialization of our first isomorphism theorem. And so how can it prove? Here it is given that H is a normal subgroup of G. This is the symbol to represent a normal subgroup. Here H is a normal subgroup of G and H is a subset of K. Because every element of H is available in K, so we can say that this H is a because and K is a normal subgroup, so here we can say that H is a normal subgroup of K also. It means H is the normal subgroup of G. This is G. H and K, these are the normal subgroup of G, and here we have categorized that this H is also a normal subgroup of H of K. So as we want to show this configuration, so in this configuration first we will discuss on this K upon H, and after that we will discuss on G upon H and G upon K. Okay, so let's see for G, K upon H. Here K upon H, it means we want to show that this quiescent group is a normal. We will see that. To show this quiescent group is normal, we will prove the property of normal subgroup, which is XA, X inverse belongs to N. You know that this is the well known property to prove that this N is normal subgroup. As we know that this quiescent group, it is the element of cosets, left cosets or right cosets. Here we are discussing only on left coset. So here we have assumed that there are two elements, K upon H and G upon H. This is the definition of quiescent group, in which we will take the elements from left coset. So this KH will belongs to this quiescent group and this G upon H is belonging to this. We have assumed these two elements. Now we are taking the composition of these elements in this way, because this is the general element and which is belonging to a quotient group which is over G, and this is a particular element or a local element which is belonging to a quiescent group over K. So here this local element is generalizing with these two generalized elements, and we want to show this type of relation. This element is written here, and this general element which is from G is written here 2 times XA X inverse in the pattern of XA X inverse. And now here we are applying the property. First we have applied here the property of inverse property, and we know that the inverse of H inverse is equivalent to H, and it will be H inverse equal to H. Here the inverse will be distributed directly from here, and the inverse will be applied only on G. After that you will apply the property of normal subgroups of subgroup here, in which we know that if there are two elements XH and YH, that will be equivalent to XYH. Now we have multiplied it. Now we will associate with this G. Again we are applying the same property here, and we will find GKG inverse is belonging to H. As we know that this is the closure property, because the composition of every element is available in G, so this is the element of G. So you can say that this property is being satisfied here. X inverse is belonging to N, and this property is being satisfied. So this part K upon H is a normal subgroup. This quiescent group K upon H is a normal subgroup of G upon H, we have stated here. Now we will define a permutation phi, because here we want to prove the third isomorphism theorem, and in which the mapping of this is available in this G upon K. So we will discuss or define a mapping phi, and such a way that the mapping of G upon K is available, G upon H is available in G upon K. So this is our assumption. We have assumed this property, and as per this assumed property, this result will be will be true, and this is because this G upon K is onto, and the mapping of G upon H is available in G upon K, so G upon K is also onto relation with GH. So here we can say that this phi is onto from GH to GK. Again, we will show that this phi, mapping phi, is homomorphism. So in homomorphism, we will see the mapping of the composition of two elements must be equivalent to the composition of their individual mappings. So here first we will apply the property of cosets. G1H will be multiplied by G2H, and this G1 and G2 will be written separately, and the H will be written as H. H into H will be written as H. So this will be equal to G1 GH. Now here we are applying the property of phi, and this result is also discussed in our first isomorphism theorem. In that first isomorphism theorem, we take the mapping of GH in GK, where because H is the subset of K, so the mapping of the elements of GH will be available or equivalent to will be available in K, that will be equivalent to GK. So here this H will be replaced by K when you are applying the definition of phi. Again this K will be distributed twice. This is the reverse of this property. As we have discussed this property, this is the reverse of this property, GK. Now this K will be replaced by H when you are using the term phi. So we have introduced here the term phi. So at this step we can say that this phi is homomorphism. Phi is homomorphism and phi is also onto, so we can say that this phi is epimorphism. Now we are going to write the statement of first shifting theorem, isomorphism theorem, and in first isomorphism theorem the quiescent group G upon H will be equivalent to G upon K over kernel of phi. Now to prove this theorem, we will show that this kernel of phi is equivalent to G upon K. So this is our last target, to show that this is equivalent to G upon K. For this we have assumed an element GH in kernel of phi, and we are here writing the definition of applying the definition of phi, as we know that this will be equivalent to mapping of G and with K, and we know that this K is kernel, so the its element will be mapped on identity, so no element will be appeared here, so it will be written as K. So this will be equal to K, and as per this property we will say that G belongs to K. If this G belongs to K, on multiplying both sides by H, we will get this G upon H, that will be equal to K. You can say that GH is an element which will be equal to KH, and KH can be written as KH upon H, and we know that this H is the subset of K, so this resultant will give K upon H, K oblique H, this K upon H, so this result will be true here. So here first we have shown this relation that every element which is available in kernel, because here we have assumed that this GH is the element of kernel, and again we have shown that this GH is the element of K upon H, so all element of the kernel of phi is the subset of K upon H, because the all elements of kernel of phi will be available in K upon H. Reversely, we will show that we will assume an element in this K upon H, and we will show that this element in kernel of phi, so that we can say that the kernel of phi is equivalent to K upon H. Now you will use this definition or this result in our previous relation which we have discussed on the last slide. So on substituting this result in the given result, this result is proved. So in case of any difficulty to understand this theorem, you can contact me. This was the last audio video lecture of your course, and from tomorrow we will discuss only on our doubts through the live sessions. Thank you so much.